In this screencast, we're going to look at the logarithmic vector space. It's a vector space a little different than most of the vector spaces we've seen so far. The idea is we're going to take the set of positive numbers, and we're going to show it's a vector space if we redefine the way we add and multiply by scalars. The idea is we're going to add by multiplying the real numbers. So the idea is to take a real number that's positive. So think x is bigger than 0. Y is bigger than 0. And if I take a number that's bigger than 0 and a number that's bigger than 0, then their product is bigger than 0. Well, that right there shows me that vector addition, defined in this funky way, I'm going to write x plus y is x times y, but in order to help me avoid confusion, I'm going to stick a circle around this vector addition symbol. That way I don't get completely confused by what's happening down below. But the idea is I take with two vectors in here and notice that the sum provides me with another vector that's already in that set. That is why it is closed under addition. Okay, now what we're going to do is we're going to take a scalar. So c, this is any number between minus infinity and infinity, and x is a number that's bigger than 0. And if I take a number bigger than 0, I'm going to define scalar multiplication to be exponentiate. I'm going to take x and I'm going to raise it to the c. Now notice that you can take any positive number, raise it to any number at all, and you end up with a number that's positive. Hence it's closed under scalar multiplication. So currently what we have is we've got a vector space, or a set of vectors together with a way of adding them and multiplying them. Any of you who've ever done natural logarithms of data, you collect some data and then start taking natural logarithms, you've used essentially this vector space in the work that you've done. Now remember, a real vector space is a set that has the closure properties together with a whole bunch of properties. We've got 4 related to addition, 4 related to scalar multiplication. We're now going to go through and show these. We're going to show associativity, commutativity. We need a 0 vector, an inverse. We need to distribute across vector addition and scalar multiplication. Got to be associative, and one has to do nothing. So what we're going to do is proceed. First, we're going to take some vectors, in particular 3 vectors. And we need to show that no matter where I put the parentheses, I get the same thing. So I'm going to compute in 2 different ways this sum. I'll put the parentheses on xy first and then put them on yz second, and let's see if we get the same thing. Well, remember that the vector addition results in multiplication, so that's just xy. And then I'm going to add z. This vector addition results in multiplication. So really that's just x, y, z, and it doesn't really matter where you put parentheses there because we're dealing with real numbers. Here we do the same thing. We've got x plus yz, and then that becomes multiplication, x times yz, and lo and behold, those are the same thing, which means vector addition is associative. We now move to commutativity. If I take x and y and I flop the order, do I get the same thing either way? We'll add the circles to help us out. This means find yx. This one becomes yx. Remember, we're just multiplying. And notice that this can be rearranged because multiplication of reals is commutative. Those two are the same, which means we're commutative. I now need a 0 vector. How am I going to get a 0 vector? I'm going to claim that the 0 vector is 1, and that's it. Why? Well, what is 1 plus x? The plus is multiplication. That's 1 times x, which is just x. So adding 1 does nothing. Similarly, if I take x plus 1, well, that's the exact same thing as x1, which is x. So 1 does nothing. Odd. The 0 vector is 1. Well, now what we're going to do is we're going to look at what are the additive inverses. If you have a vector x and you times it by -1, we'll come back up to this scalar multiplication. Scalar multiplication says I should exponentiate by -1, which means it's 1 over x. This is the inverse of x. To show it's the inverse, all I have to do is add them If I add these together, I get 1 over x. Remember, addition is multiplication, which is 1, which is the 0 vector. Similarly, you get the same thing if you do x plus 1 over x, which is just x times 1, which is, again, it's 1. It's x times 1 over x, which is 1, which is, again, the 0 vector. So we have additive inverses, 0 vector, and addition holds. We've got all 4 of those axioms holding. We'll now jump to scalar multiplication. If I take a scalar, now remember this can be a number, any real number at all, and I multiply it by an x plus y. I'll put circles around it to remind us what the operations are. First, we'll do the thing in parentheses. The whole point to this one is I need to show that I get the same thing if I do cx and then cy and then add. Well, let's just check both. Here, if I add first, which means multiply, then that's xy. And then I'm supposed to multiply by c. C means exponentiate, so that's xy to the c. We now come over here. C means exponentiate, so this is x to the c, and then I'm going to have to add, this one is y to the c. Well, that addition means multiply, so that's x to the c, y to the c, which is xy to the c. That is the same. So we now see that the scalar multiplication distributes across vector addition. What if I take the sum of two scalars? Now this positive sign is actually in not this set, but this is actually the real number addition, because c is any real number. And then I multiply that by some vector. Well, that's the same thing as x. I need to exponentiate by c plus d. I'm just going to expand that as x to the c, x to the d. Well, what happens if I first multiply dx and then add? So here I have an x to the c, here I have an x to the d, and then I add, but that addition means multiply them together, so we get an x to the c, x to the d, and that is the same as that, so the first two hold. Now we look at what happens if I do c times d, where this multiplication is in the real numbers, and then I times that by x. Well, that means let's take x to the cd. Similarly, what if I do c and then multiply that by d, which is multiplied by x? Well, this one means exponentiate, take x to the d, and then we're going to multiply by c. Well, that means let's take x to the d and let's exponentiate that to the c. But when you exponentiate an exponential, you just multiply the terms together, and those two things are the same, hence that third one satisfies. Now if I take 1 and I multiply it by a vector, well, that's the same as x to the first, which is x, which means multiplication by 1 does nothing. So that completes the screencast and shows that the logarithmic vector space is a vector space. The whole way we define vector addition and scalar multiplication is a lot different than what we're used to when dealing with vectors in Rn, but we have something that is a vector space. And that completes the screencast.